Sit back, relax, and enjoy the wonders.
Show made by Seb Lee Dalal, part of a show called Polaris. So let's have another huge round of applause for Seb and the Lasers.
I'm Miodownik. I'm an engineer here at UCL, and this is...
I'm Helen Czerski. We're in the same department here, so I study the ocean, but I'm in the Department of Mechanical Engineering along with Mark, and we are just one. Our department is quite big, but it's still just one small part of the whole faculty of engineering here at University College London, and there is so much of it.
There is. There are 10 departments, there's over 1,000 staff, there's more than 10,000 students, and we've been doing this for a long time on this site. We've been doing this for over 190 years. In fact, the first professor of civil engineering was established here in 1827, would you believe?
We have been busy, and engineers have done a lot of things in that time. As you saw in the video at the start, engineering is behind almost everything that we see and do. It takes scientists have ideas and test out the theories, but the engineers make it happen. And that is a big deal. And so throughout those years, it's not just the engineers working in companies that are making a difference. There are academic engineers testing things out. All of our collaborators, they have bits and pieces in their offices. They're playing with the world in order to make things happen.
And you sort of head scratch, you go, what is engineering? And it's actually very difficult to kind of say what isn't engineering. That's kind of an easier place to start. I mean, all this building, these lights, that laser show, music technology, video technology, film technology, TV technology, that's all engineering. And it just goes on and on. There's space technology, there's aerospace technology, there's automotive, and we do all of it here at UCL.
So we want to share it with you. So we know that we don't know who is out there in the audience. Actually, we can't see whether you're there at all, apart from the cheer, because it's the bright light shining in our faces. But one of the most important things about engineering is that it is becoming more and more about people. And we recognize that these things are done by people, but also they impact people out in the world. That's all of you. All of us are impacted by all of this. And of course, as we're developing it, it's really important to listen to the people who might use it, to listen to the people who might be affected by it. And so more and more engineering, kind of used to be seen as this dry thing of technical, you work in your shed on your engineering. Now we want to be out there in the world, and the point of this evening is that we want to share some of the best of the engineering we have to offer with you, so that you know what it's like, and you can go out into the world and tell all your friends how cool engineering is. Yeah, and you'll see the engineers from our faculty presenting the work to you, and you'll see they're like you, they're like all of us. They are people. They represent the whole diversity of humans. Some of them wear flowery shirts.
Yeah, I mean, that is a minority of the population, but important to represent them, and I'm proud to do so.
So there are many types. So we've got loads of things lined up for you. There's a whole mixture of things tonight. There's kind of things to do with space, things to do with the human body, things to do with the internet. There's a huge variety, and we're really excited for you to see it. So it is pretty much time to get started. We've talked about lots of types of engineering: civil engineering, chemical engineering, biochemical engineering. But one thing you might not think very much about, and it is quite a serious subject, is fire engineering. So let's start with Michael Woodrow and our fire engineering.
Hello everyone, my name is Michael and I'm a fire engineer, and I'm going to tell you a story about how I ended up in South Africa helping a group of artists create an enormous fire tornado in the desert. It all started a couple of years ago when I was asked by an architecture colleague who was tutoring at the Bartlett School of Architecture here in UCL. Could you teach some of my architecture students how to design a fire-safe building? I said, of course. I run the fire-safe design program at UCL. It's literally what I do. And they said, great, you have 1 hour. What am I going to do for 1 hour? So I thought about it, what am I going to teach these students in 1 hour about designing any safe building? And then I finally came up with an idea. I wasn't going to teach them anything. I was going to set the students a challenge. So I stood in front of the students and I told them, I want you to figure out how to burn your building down with a single match. Because it's actually really hard. And if you know everything if you understand all the science of how flames grow, how they spread, how you're able to make that fire move through your building and design it in exactly the way that you want it, you can switch it off. But it got me thinking, and it reminded me of this student I'd met about a decade ago who had decided to do his final year dissertation on designing the burn for the Temple of Transition at Burning Man in the US. It was a mad idea. But it got me thinking, this student had this incredible idea to talk to the designers, the artists of this enormous temple called the Temple of Transition in Burning Man. And the idea was for him to actually help them design the burn in a way that could be more beautiful as a piece of art than this is more beautiful as a piece of art than the structure had been standing in the desert for the week beforehand. So here you can see the Temple of Transition on the top left, Alex on the far right, the student, very happily holding his Burning Man ticket. But it got me thinking, why can't I do this with our students? So I jumped on my computer and I looked up. Turns out there's a group called Africa Burn. They're in South Africa, so I emailed them. And I said, how would you feel if we worked with your artists to help design their fires, to make these beautiful fires. And I got an email back almost immediately saying, we got no idea what you're offering, but let's have a chat. Right? So we jumped on Zoom. It turns out these guys are incredible. They're a non-profit organization. They do some incredible work in South Africa. And every year they host a festival in the middle of the desert where 10,000 people turn up and they build beautiful pieces of artwork. They have these crazy mutant vehicles. There's lots of fire everywhere. And then they even create these enormous timber structures. Right, the one on the left-hand side, this project had about 8 tons of wood from old pallets that was totally unusable for building construction. At the end of the week, they burned it. But when it came to the burn, the only thing that really seemed to matter was how much petrol are we putting on it. So this one on the right, for example, took 75 liters of petrol. The year after, so by this point, I've actually gone out to Africa Burn with my wife and to see what it's actually like. And by this point, I'm learning so much that I decided, how about we work with an artist? So we got put in touch with the artist behind this installation. It's called The Tree of Stories. You can see on the left-hand side here, me with the cowboy hat, and the burn boss here, Rob, who's taken the photograph. And this incredible structure was built in 2020 to be burned. Unfortunately, wasn't able to due to COVID. It sat in the desert for 3 years. This thing is ready to go, right? Okay, and it's been sitting there. Not only is it this incredible structure, but it's just become this focal point of the whole institution. In the evenings, in the early hours of the mornings, with people raving at night. And all of these stories have come together, and they're all imprinted. They're a part of the artwork. It's called The Tree of Stories for a reason. And the idea is to send this cathartic message as it heads off into the sky. And I asked the artist, what sort of fire do you want? And he drew this picture. He said, I want a fire tornado. I'm like, cool. So most people don't realize that actually nothing burns in its solid state. Nothing even burns in its liquid state. It only burns in its gaseous state, which means that if you take something simple like a candle and you blow out the flame, that plume of white smoke you get off the top, that's not smoke. That's pyrolyzed wax, which means you can do this. Something to try at home later, right? All that needs to happen now is just an air entrainment, a shift in the air entrainment to cause the air that's coming into the base of the structure to swirl. It's perfect, it's ready to go. And so we got the students involved, obviously. They built this incredible model, and we even burned it at the back of the UCL Estates fire team's offices with consent and risk assessment. You can start to see here the tornado is just starting to go. And then I actually had to fly over to South Africa. At this point, the butterflies are starting. Look at the size of this thing. This is where the fire is going to go. Okay, so you can see on the left-hand side this enormous pyre that they created. And we introduced these metal sheets to try and force the air to move in the direction that we wanted to. And so at this point, I'm getting kind of nervous, right? So at night, we have the fire is ready to go. We have the match. It's a big match, but it's still a match, right? That one match goes into the structure. And remember, the previous one took a huge amount of petrol. This one just took 2 shot glasses of petrol just to get it going, right? And then we're sitting there, fingers crossed, will it go, will it go? And then all of a sudden, it really went. It really, really went up. And I'm sitting there going, oh my goodness, it's gone completely wrong. And then something incredible happened. It started to kick out vortex shedding, one after another, after another. It transferred all the way across the 70-meter radius where they had people waiting in the front row, getting hit in the face with these hot gases as they were coming through. Everyone was absolutely loving the tornadoes that are coming off. And in the end, we failed miserably at producing a fire tornado. We made 23. And it just kept coming. And in the end, the fire came down, it started to fall apart, it died. And at the end, the day after, the artists went and they picked up every single piece of charcoal, every single nut and bolt, and dug up the little pieces of concrete at the bottom. They took it all away as part of the leave no trace philosophy of the Africa Burn movement. Which brings me to my final point. So I just put in a couple of weeks ago a funding application to bring a student to Africa Burn next year to help me burn this. So my only question to ask you is, who wants to help me burn it? Thank you.
Fire engineering. I mean, you know, this is just one of many extraordinary things going on at UCL in this Faculty of Engineering. And I want to talk to you a little about the next speaker, and because it's another just incredible character, like almost cartoonish in his sort of superpowers. When I first came across him, he worked as a doctor, air ambulance, and saving people's lives. And it's just all these epic kind of stories he would tell me about, you know, these things that you have to sort of fly to and land and get someone in the ambulance. And I was like, wow, it's incredible. And then the next thing I know, I'm watching TV, and he's advising NASA on medicine in space. And he's off there in America doing all that stuff. And I'm thinking, God, this guy is incredible. And then the next thing I know, he's back in the UK. He's presenting a TV program. He's doing radio programs. He's a broadcaster. And then the next thing I know, he's here at UCL again, this time a professor in the engineering faculty. And then, backstage, I realized he's still doing all these things. He's an absolutely extraordinary guy. His name is Dr. Kevin Fong. He's a medical doctor. He still does air ambulance. He still advises NASA. He's still doing broadcasting. And he is about to come on and tell you about some other amazing stuff that he's doing. Dr. Kevin Fong.
It's a very lovely introduction from Mark. Thank you so much. So I am Kevin Fong. That is my slide that's dying out there. I am a doctor. I've done everything I've done in my life has been completely by accident, to be honest with you. I studied astrophysics here because the University College Applications Handbook is alphabetically arranged, and then I sort of accidentally went to medical school after that. Eventually, I went to NASA. I worked with NASA, but at NASA, they're not interested if you're an astrophysicist or you're a doctor. They want you to be an engineer, and so eventually I had to do a degree in astronautics and engineering and space engineering, and so I did this. This is me on the Vomit Comet in 1998 while I was still a student here. This plane flies along at 25,000 feet, about 3/4 the speed of sound. It goes nose up, climbs 10,000 feet, goes over the top, dives 10,000 feet, and you're weightless for about 23 seconds. So you're flying around like that for about 23 seconds. It does that 45 times in an hour and a half. And it is amazing unless you're sick on the first parabola like this guy was, and it's just like the worst roller coaster you've ever been on. I was going to tell you about my efforts to become an astronaut and how I failed to become an astronaut. I applied through European Space Agency. There were 24,000, 23,000 applicants, and I got through quite a few rounds. I got down to the last 90 people, but I failed. But you know what? I realized that you don't really want to hear from me as a failed astronaut. You want to hear from a real astronaut. And today, we were lucky enough on the campus to link up with the space station with my friend Mike Barrett. But really, after all of that, talking to me is like going to the Republican National Congress, wanting to talk to Donald Trump and finding Nigel Farage. So instead of talking to me as a failed astronaut, you are going to have a chat from a real astronaut. This is my very good friend, Dan Tarney, who is a twice-flown astronaut. He flew STS-120. He flew Expedition 16. I was lucky enough in 2007 to see him go into space. He's walked in space 5 times, and so give it up. Astronaut Dan Tarney.
Thanks, Kevin.
So Dan, we're going to have a little chat here. So what I want to know is why does NASA love engineers so much? Because of all the qualifications it loves for its astronaut candidates, it loves engineers, and you're an engineer. Tell me why.
So, yes, I'm a trained engineer. As a mechanical engineer, I went to college in America and studied engineering with no intention of going to space. When I studied engineering, I liked building little stuff. I liked the small things about engineering and knowing how they work and making them better. And only, I would say, out of serendipity did I start in the aerospace industry back then at a big company making satellites and stuff. And then as things went along, I thought, you know, I should try to become an astronaut because who wouldn't, just like Kevin? And I had these dreams, and I was just lucky to get all the way through. Why do they like engineers? Well, when you're working in space, we are in a very first of all, you get in a very complicated vehicle to go up into space, a rocket of some sort, the shuttle in my case, or the Soyuz, or the Dragon, and then you go live in something in space on the space station. It's very, very complicated. It's really a very complex machine. And even when we do spacewalks, we get in a spacesuit, boy, that spacesuit is really complicated. We don't have to know how to design it. We don't have to know every little detail about it, but they like engineers because we know enough about it to understand the basics of how it works. How does heat get transferred from my body out into space? We don't have to know exactly how it works, but we have to know that that's a very important system and basically how that works. How does energy transmit from the sun to the solar rays to the batteries to my iPod, right? It's not critical that I know all the details, but when they hire engineers as astronauts or, of course, to work at NASA, we have a good basis for understanding how basically things work and how complicated things interact, how systems interact.
Now, I'm going to ask, because I'm sure everyone's dying to know, you have flown on Space Shuttle, you've launched off the deck. Just quickly for me, how fast do you have to go, 0 to what, and how quickly, and what is that like? You've ridden that thing.
So I've flown the Space Shuttle a couple times, and so we lie on our back in the Space Shuttle because we launch, my friend says, pointy end up, nose up, right? So we're lying on our back, and we're going 0 miles an hour relative to the Earth, and then the countdown goes, and you can't hear them say 10, 9, 8, 7, but we in the cockpit are going 10, 9, 8, 7, 6. And when it hits 0, depending on the type of rocket, the Space Shuttle at least, has 2 big solid rocket boosters, and they ignite. Boom, you're going to go somewhere. It feels like, boom, feels like you just kicked in the backside. And there's, of course, a great amount of force on your body and a growing amount of force. It's like you're in the best sports car you've ever been in. And you're pressed back into your seat. And so it feels like somebody's grabbed you and is pulling you, yanking you into space. Because you weigh so much on the launch pad, you actually aren't accelerating that much just off the launch pad. But every millisecond that you're flying, you're losing propellant. So you're getting lighter and lighter. And as you gain altitude, you're going through less and less atmosphere. So the accelerations are greater. For those first 2 minutes are just, I'm not going to say violent, but really there's a lot of shaking. And you really have to concentrate on the gauges, make sure you understand what the spacecraft is telling you. And then for the Space Shuttle, at least, the solid rocket boosters come off, and now you're on liquid engines, which is a much smoother ride. And now it just feels like somebody's stepping on your chest harder and harder and harder. And you know you're going to be okay. It's only 3 Gs. But it's really interesting that it's the pressure on you, the force that is being pressed on you because you're accelerating. You have to consciously breathe. Man, and then you think, how can I reach out and grab this thing? And you can, but it takes a lot of effort. Really interesting. So that's for the next 6 minutes. And then when the computers know that they are exactly at the right speed, boop, all the engines turn off. And now, it didn't, somebody told me you're going to feel like you're falling out of your seat. And it didn't for me because we're strapped in tight. But I looked forward, and my friend was the pilot on that flight, and he held up the procedure book, and he goes, hey, look at this, and let's go. And the book was just floating there in front of him, and that was like, wow, we are in space. So 8.5 minutes, 8.5 minutes from sitting in Florida on the launch pad to going 17,500 miles an hour, going around the Earth every 90 minutes. It's a great ride. I recommend it for any of you guys. Yeah.
We have only got 1 minute here, but we've got a slide up. We've got a slide up here of you on a spacewalk. I remember watching you do this on NASA TV. Just in the minute that we've got left, this is an awesome experience. Just describe what it's like to be out there in the blackness of space wearing that.
Yeah, so the suit you have to wear, it protects you. It's your life. It protects you from dying out in space. So it has a couple jobs. It has to keep pressure on you. It has to keep you cool. It has to provide you oxygen. It has to remove the carbon dioxide that you exhale. So it has a lot of jobs, and it weighs 300 pounds, 120 kilos here on Earth. But of course, in the weightlessness of space, it's bulk that you have to move around as you move around the space station. You open the hatch and you float out. You're clipped in, of course, but as you hold onto the space station, you're going 17,000 miles an hour, just like the space station. And you look at this beautiful structure that we've built out in space, and then you look at your feet, and 200 miles under your feet, oh, hey, there goes Ireland. That looks pretty cool. Or Italy or Chicago. we're out there to do a job. We are conscientious that that's what we're there for. We have to do the bolts and do the everything that we're supposed to do. But boy, the privilege of doing it out in space is just fantastic.
Dan, it's been such a breakneck tour of it. There's so much more to say. We're out of time here. I'll just finish with, when I got down to the last 90 candidates in European Space Agency selection, I had to have a chat with my family, because like then it's almost possible you get selected. Dan talked to me about this the first time I applied. And so my wife, my 18-year-old son who's going to university, he didn't care. My wife really didn't care. My 14-year-old, I had to sit him down. I said, look, Noah, if I get selected, I'm gone. I won't be there for the last 4 years of your school life. You will be missing a father for all of that time. You need to be okay, and if you're not okay, I will drop out of process. And he looked at me, and he turned around, and he said, yeah, but you'll be an astronaut, innit? So the bragging rights make up for the absence of the father figure. Thank you very much. Cheers.
Thank you very much.
Okay.
The stories. We could clearly
Very
spend the
good.
whole
Very good.
afternoon,
Very good.
whole evening listening to how fabulous that is. And that, what a privilege as well. You know, we don't have that many astronauts here in the UK, and it's a real treat when you get to hear what it's really like from the horse's mouth. So engineers help us and mankind look out into the vastness of space. But engineers also can help us look inside ourselves, from the very biggest to the very smallest. And so next, two people are going to take us on that journey into the inside of ourselves. And please welcome to the stage to do that, Peter Lee and Claire Walsh.
We saw outer space. We were taken to outer space. As Helen said, Claire and I want to take you to the inner space, the inner universe of our body. To do that, we came up with a revolutionary new X-ray imaging technique that we call HIP-CT. It's a technique which was developed actually during lockdown. What happened was we got a call from our medical collaborators in Germany, and they thought that COVID was doing damage to the lung, but at a microvascular scale, but they needed to image that and the whole lung. This had never been done before. And so what we did is come up with a technique that we applied to COVID, and since that, in the past 4 years, dozens of other diseases, all the way from Parkinson's to cancer. Now, X-ray imaging isn't new. It's been around for over 100 years. Here's the first picture and radiograph that was ever done of the inventor's wife's hand. In the past 100 years, it's become better resolution, digital, and actually Hounsfield in the UK in 1971 made it 3D by inventing tomography, or CT. But the CT resolution is actually only about 1 millimeter. That's about 1/10 of my finger. It's not all that great. And it really only resolves bone or hard tissue. It doesn't really show the soft tissue around it, as shown in this image here. So what we did with UCL is work with the European Synchrotron Radiation Facility, or let's just call it the European Synchrotron for ease, and let's fly out there. It's in the French Alps, the southern French Alps, and a synchrotron is a particle accelerator. It's bigger than Wembley Stadium, this synchrotron, and it does only one thing. It takes electrons and accelerates them up almost to the speed of light. So though we're looking really small, at least something's going as fast as those astronauts, and that's the electrons. The electrons only want to do one thing when they're going that fast. They want to go straight. And they're going so fast that they're relativistic, aging 20% slower than us. We take them and we bend them, and those blue dots, which are the bunches of electrons, shed synchrotron radiation at a wavelength from near infrared all the way to hard X-rays. And the synchrotron had just undergone a €100 million upgrade, which gave it all sorts of other features that Claire, myself, and Paul Taffero, who works there, went through and turned into a technique called HIP-CT. Well, with that lead on, why am I so enthusiastic about it? Well, let's look at classical CT. This is one of our hearts, a human heart with CT. The resolution's about 1 millimeter. You really can't see that much. MRI gives you better soft tissue resolution, but again, 1 millimeter or so resolution. This is HIP-CT. It goes through and has 10 micron resolution. That's 1/10 of a hair instead of 1/10 of my finger. Why is it important? Heart disease is the #1 cause of death in the UK, and actually worldwide as well. But hip CT doesn't stop there. Hip CT goes way beyond. We can zoom in particular areas without biopsying and see all the way down to a micron. It's 1/100th of a hair, or 1 billion times more information in 3D. And that's to see for the first time individual muscle cells, or myocytes, where they are in 3D in the entire heart. And then for diseases like arrhythmia, lets you correlate what you're seeing now, for the first time ever, the thin structure of the conduction system in the heart, visualized in 3D. That's the electrical system of the heart that triggers those muscle cells and keeps it beating and keeps me happy up here. Why is that important? Arrhythmia, irregular heartbeat, that, once we understand the conduction system, we could treat better. And we're not really going to just look at the conduction system. We're looking at the hearts, working with cardiologists worldwide, biologists, radiologists, and anatomists, to look at the heart in health, disease, and as we age. But we're not just stopping there. We're going and looking at all of the organs, from the cellular level all the way up to the whole body. And I'm going to hand you over to Claire Walsh, who's going to tell you how that impacts on the brain. Claire.
Thank you very much, Peter. I'm going to talk to you now about how hip CT is helping us develop some of the most detailed maps of the human brain's wiring ever, and how those maps can help neurosurgeons treat diseases like Parkinson's. First, I'm going to tell you about something called deep brain stimulation. So deep brain stimulation is a surgical technique where an electrode, like this one I have here, is implanted through the skull of a patient deep into the regions of the brain, and it's targeting faulty wiring circuits in the brain that have been affected by a disease. We target very deep brain regions. One of them in particular is called the subthalamic nucleus. It's about the size of a grape, and you can think of it like a junction box of the brain. It has lots and lots of wires all coming together in a small space. When the electrode is correctly implanted, it sends impulses that help regulate those wiring systems, acting a bit like a pacemaker for the brain. And this can have some really amazing results. Here you see a patient with Parkinson's, and in a minute they're asked to shake their hands as fast as they can. With the electrode off, it's very difficult for them to do this motion, but with it on, they can do it quickly and in control. But as with any surgery, precision is paramount. Getting this electrode not just into that grape-like junction box, but into exactly the right part of it to target the correct wiring system is what enables you to get good clinical outcomes for these patients. It's a little bit like trying to take this electrode, put it into King's Cross Station, but only target the Victoria line. So let's push this analogy a little bit further. If a patient comes into hospital to have this procedure, they're going to have an MRI scan taken to begin with. That's like this Google satellite image. Now remember, the goal of the surgeon is to take an electrode like this, put it into King's Cross Station to target just the Victoria line. Quite challenging, I think you'll agree. What the neurosurgeons and teams use is a map. If you overlay a map of the brain that shows you exactly where those wires and big structures are, you're much better able to plan and precisely implant the electrodes. But where do you get a map of the brain like this from? Well, you can't actually get it from those MRI scans that the patients have. They're nowhere near detailed enough to give you the information you'd need. Actually, what you have to do is you have to take a brain that somebody has done the amazing gift of donating to medical science after their death. These brains are then subjected to really detailed anatomical analysis that allow you to understand where, on average, these structures are within different human brains and create a map. This has been done for hundreds of years. For example, this one in 1908 by Brodmann, based on just 2 human brains. One of the most advanced maps out there in the world at the moment is one made in Germany by taking a single human brain, slicing it into 7,000 slices and digitally reassembling them. It took over 5 years for the team to do and has never ever been repeated since because it was so challenging. Hip CT is helping us create the next generation of these brain maps. This video that you can see here of a whole human brain, it was taken in a matter of hours, not weeks. It has the same level of detail as that 7,000 slice brain, and what's more, we didn't have to cut it up, so none of those 3D structures have been distorted. As we go deeper into the brain, as Peter showed, we can see more structures. That light gray is the white matter, the wires we're interested in. You can also see gray matter, the computing parts of the brain, and blood vessels, and even new things that no one has ever seen before. As we go through, I want you to look at those white matter, those wires, the light gray, and hopefully you can see as we're zooming through the brain here, how they make up a wiring pattern. In a minute, you'll see some really nice vertical wires there, kind of obvious to pick out. What we're doing as a team now is we're using advanced artificial intelligence to outline these wires in the brain automatically to create the maps. As we do this for more brains, we put our data into the existing maps that neurosurgeons are already using, so we improve upon what's already there, make it better detailed. But crucially, we can put in the maps from many, many individuals' brains. So this means the maps that the neurosurgeons use every day can better reflect the individual variation in our population. You can see by this, HIP-CT is not just a fun anatomical tool. It's something that we can really use to help clinical practice treat individuals better. Thank you very much.
Thank you.
Incredible, incredible, don't you think? And of course, you know, this idea of like, where does engineering stop and kind of fiction begin or kind of fantasy begin is an interesting one. In fact, arguably, this is really why a lot of engineering happens, actually. Someone has a crazy idea, or someone makes a joke, and then someone else goes, but actually, could we try that, perhaps? And I want to just tell you a bit about my research, because it sounds a bit mad, and you're probably sort of thinking, is he reliable at all up there? And so I just want to tell you a little bit about what we're doing in our lab. I'm a material scientist, so I make new materials. That doesn't sound as exotic as half the stuff you've already heard today. But let me just tell you about what we're trying to make. We're sort of concerned by the fact that so much of the modern stuff in everyone's hands, like your phone and your laptop or all the things in your house, they don't last very long anymore, like your trainers. They break, and then you can't really repair them. So you have to throw them away and buy a new one. And that seems like just this kind of incredible treadmill. And it's very expensive too. So why is that? And what could we do something about it? And well, when you think about why some of these things break, like your phone, the phone screen, for instance, you drop it. Well, that's obvious. You dropped it and there's a crack. And well, that's not your fault, is it? I mean, things like that happen. And it's not the phone's fault either. I mean, they did their best. But, you know, material scientists like me think, but actually, that isn't how the body works. That isn't how humans work. If you break, if you have an injury, you heal yourself. You know, if you have a bad injury, you might go to hospital, or you might go to bed, but you'll heal yourself. Couldn't we make phones? Couldn't we make materials that heal themselves? Is that fiction? Is that crazy? And so there's a lot of people, including us, trying to make this a reality. And already out there is something called self-healing concrete. So already you can now build bridges, and people do, and tunnels out of concrete that when it gets cracks, it heals itself. And you might think, well, how does that happen? How does that work? And the answer is that inside that concrete, the makers of the concrete put tiny bacteria that sleep. They fall dormant as the concrete is laid, and it's only when a crack is opened do they wake up. And then they might have been in there for 10 years, but nevertheless, they're viable, it turns out. And the concrete manufacturers put little bits of food in there, starch packets, and they eat those, and they exponentially increase. And they do a poo, it turns out, these concrete bacteria. And their poo is something called calcite. It's a mineral, and it's one of the main constituents of concrete. So they eat their way out of the crack, and they leave a perfect concrete behind them. And the structure retains 90% of its weight, of its strength. So it's incredible that these things are already in these kind of worlds. But could we do it for the phone, you ask? Could we, could the next bit of phone technology is that you crack your screen and instead of thinking, oh my goodness, I've got to go to the repair shop and they're going to charge me a fortune, or should I get an upgrade? Should I just, ditch it? No, you put it to bed, you give it a little Lemsip, and in the morning that crack is healed. And these materials are called animate materials. They're sort of lifelike. And that's the kind of stuff that we're developing in our labs. And, if you think it sounds science fiction, that is what people said 50 years ago about phones themselves, about the idea that you could have a phone, about the internet, about space. So these things happen, and this, I am absolutely sure, is going to happen. And of course, when they happen, Well, probably the next thing will be that the problem isn't that our phones break and we have to throw them away, or our trainers break and we have to throw them away. Probably that all of those things in our lives, we'll get used to them just healing themselves, and we'll get absolutely used. And then they'll start to have diseases. So your trainers might get cancer, and then they might have to go to a real doctor and be healed. And that sounds mad, doesn't it? But I'm confident that actually cancer of the bridge or cancer of the tunnel is probably something that future generations will have to face. And talking of solving cancer and that kind of thing, of course, that's the kind of research that goes on in this engineering faculty too. And I want to introduce you to Kazim and Beatrice, who are going to tell you a little bit more about that. Okay, Kazim and Beatrice.
Good evening. My name is Kasim Rafiq. I'm a professor in biochemical engineering and the Vice Dean for Health in the Faculty of Engineering here at UCL. And I'm joined by Beatrice, one of our fantastic early career researchers. And tonight, we're thrilled to share with you the transformative impact that engineering plays in revolutionizing healthcare. Now, when I think of the future of healthcare, this is what I think of. The idea that we can develop truly personalized therapies that are both safer and far more powerful, and we can start to dream about curing things like cancer. And working with leading US clinicians and also clinicians here at the UCL Royal Free Hospital, we're starting to make that dream become a reality. This is Emily Whitehead. When she was 9 years old, she was diagnosed with acute lymphoblastic leukemia. This is an aggressive form of blood cancer, and the normal treatment option is that you're delivered a bone marrow transplant. Emily had this and it failed. The second treatment option is multiple rounds of chemotherapy. And as you can see from the image, Emily had this, but it too failed. And the third treatment option is, there is no third treatment option. She was destined to die of her disease. That is until the emergence of personalized gene-modified T-cell therapies. It just shows how far we've come from a scientific and a clinical perspective. But it also pains me, because I know that most of the patients who currently need that therapy will not be able to access it because it costs $400,000 per dose. And at UCL Engineering, we're leading the charge in trying to bring down the cost of that by improving the manufacturing process, which is making up over 50% of that cost. So with that in mind, we're trying to transform healthcare by developing these truly personalized therapies. And here's a sneak peek of some of the cells in action. I'll be going in more detail tomorrow as part of the Engineers for Change and exactly outlining how we achieve that. But here are the T cells in action. So on this video on the left here, you'll see the T cells which have not been modified from the patient and are unable to recognize the cancer cells which are in green. The cancer continues to grow and grow and grow. But on the right here, you now see the same patient's T cells which have been modified, and the T cells now recognize the cancer. It surrounds the cancer cells and it starts to neutralize them, showing the powerful nature of this therapy. And it's our goal at UCL to try and make that accessible to all the patients that need them. So that is a snippet of some of the exciting manufacturing research we're doing in medicine development, but I'll now hand over to Beatrice, who will showcase some of the incredible work we're doing in developing diagnostic tools and advancing computational models to understand diseases like dementia. Over to you, Beatrice.
Thank you very much, Kasim. So, hi everyone. My name's Beatrice and I'm a PhD student here at UCL. And I want to talk to you a bit about how we can use computational models to understand dementia. Now, as I'm sure many of you already know, the most common form of dementia is called Alzheimer's disease. It actually accounts for around 60% of all dementia diagnoses in the UK. And Alzheimer's primarily affects a part of the brain right in the center, actually kind of like dug into the middle of your brain, if you can imagine that. And it results in problems with memory. That's kind of like the classic thing we think of when we think of dementia. But there's actually many different types of dementia. Some researchers think there could be over 200 different types of dementia, dementias which affect different parts of the brain and also result in different symptoms. And I want to talk to you about primary progressive aphasia. So I'm going to break down that really fancy Latin name, because when I started studying this, I had no idea what it meant. So primary means it's the main thing. Progressive means it keeps on getting worse, and aphasia means it affects language. So this is a type of dementia which affects your ability to use language and also to communicate with others. And sadly, it just keeps on getting worse over time. So these symptoms keep getting worse and worse. Now, what I'm interested in is trying to understand brain changes in primary progressive aphasia, so specifically how the brain changes and evolves. And I do that through the use of medical imaging. So I'm going to show you an MRI now in primary progressive aphasia. Oh, if I could use the remote. So this is an MRI scan, 2 MRI scans specifically, of one person who's living with primary progressive aphasia. So on the left is an MRI scan which was taken at their first visit to the clinic. On the right is the same scan, same part of the brain, it's sort of through the back here, but this was taken 12 months later of the same patient. Now, it's really hard to spot with a human eye, and I'm definitely no radiologist, but you might just be able to see that parts of the brain are shrinking. Over time, in the left-hand side of the brain, specifically the left temporal region down the side, we start to see progressive shrinking of the brain. And this is really indicative of this type of dementia. So what my work looks at is how we can develop computational models to understand that. Computational models, I feel like, is a bit of a wishy-washy term, and I specifically use machine learning, which I think is even more of a wishy-washy term. So let me try and explain what I do. So what I do is I develop mathematical equations, and these equations kind of describe how I think the disease works, based on all the things I've read and the people I've spoken to. And then I take these equations and I compare them to lots and lots of MRI scans like this. And this is sort of a computational method. I'm not doing this by hand, I get my computer to do it. And it compares these equations to the MRI scans, and it tries to figure out how good a match they are. And the machine learning part is how it learns from this and improves my model. Now, the goal of this work is to be able to understand the disease better, and that's really what I'm doing, is improving our understanding of this condition. But we hope that down the line, this sort of research could help us to diagnose conditions like this earlier, and also maybe provide treatments. And this is really, really important, because rare conditions like primary progressive aphasia are massively underdiagnosed in the UK. And actually, just before coming on stage, I saw there's a headline in The Guardian today about that exact thing. Conditions like this, they reckon only 1 in 5 people who have it will ever receive a diagnosis. So thank you very much.
Nature, the final frontier. These are the voyages of the starship CNIE. Its 5-year mission: to explore strange, grand challenges, to seek out sustainable development and responsible innovation, to boldly go where no woman has gone before.
Good evening, everybody.
Bone, broccoli, lung. What do these items have in common?
Unique each item may be, but they all hold fundamental principles that, when applied, can be used to solve our grand challenges.
Good evening, ladies and gentlemen. My name is Marc-Olivier Coppens. I'm a professor at UCL Chemical Engineering and the director of the Center for Nature-Inspired Engineering, CNIE.
Hello, everyone. My name is Lucy Todd, and I'm one of the PhD researchers at the Center for Nature-Inspired Engineering. And today, we're very excited to showcase 4 applications that have been realized through the nature-inspired methodology. Here we have an ostrich bone. Now, inside this bone, just like in your bone and in other parts of our bodies, there are intricate networks. If we are extracting the mathematical principles behind these networks, we can 3D print accurate models of these structures.
Did you realize that Gustav Eiffel was inspired by the structure of the thigh bone to design the Eiffel Tower, at that moment, the tallest structure human-made in the world? It's a question of balancing of forces at multiple scales and realizing this at any scale and using a minimum amount of material, just what this thigh bone needs to do. and what you implement into the Eiffel Tower. Ingenious engineering inspired by nature. And it doesn't stop there. Models like this can also be used at this very small scale. In fact, a related model can be used to represent networks within our lymph nodes, which you just heard about, where immune cells, T cells, can be activated to combat disease. And models like this can then be used to see how this three-dimensional environment influences how T cells interact with each other. So based on that, we can engineer solutions to combat cancer in cancer immunotherapy.
We can print structures this big, but we can also print them to be on the size of a pinprick of a needle. Now, did you also know that you can extract mathematical principles from your dinner vegetables?
The humble but mighty broccoli. Look at this beauty. It's not only tasty, but you can pick up pieces that look just the same as the larger piece. I can pick up a few more. I'm going to steam them later. And you can notice the large piece, a smaller piece, and a still smaller piece. This is an example of a fractal self-similar networks, and they're everywhere in nature. They're there in the trees that we see around it, around the broccoli. And so these are scalable networks that uniformly distribute fluids and nutrients from the stem to each of these cells. And so learning from this, we have invented fractal injectors like this, fractal fluid distribution devices. In fact, you can distribute a fluid going from the stem to each of these outlets, equal distances, and uniform distribution within another fluid, and so easily mix them. And so for a small vessel, you would just use an injector like that, and in a larger one, you would use one like that, just like in the trees and in the broccoli, without needing extra energy for scalable manufacturing. Another lesson from nature. Trees, broccolis, and there's much more.
Now, these fractal architectures can also be seen within the human lung. Now, the human lung also has some amazing properties. It has a very minimal loss of energy when it comes to transporting oxygen, and it can be easily scalable and has a very low pressure drop. Things that are very important within
hydrogen fuel cells. So indeed, here you see another fractal self-similar structure inspired by the lung. And so we can distribute in a flow cell, in a fuel cell, on one side the fuel, hydrogen. On the other side, you have another flow plate to distribute the air, and you do this over a catalytic layer. And so the hydrogen and the oxygen electrochemically will be converted into water, clean water, and electric power. And these can then be used to power
here a hydrogen car, which may work or may not work.
Let's see.
Nope, it's decided not to work. I promise you that it does work, and it is amazing when it does.
Sometimes it is. Sometimes technology fails us, but we can make it work at another moment. So, what do we have here? And now for something completely different. The thorny devil lizard. This incredible creature here comes from the UCL, this specimen from the UCL Grand Museum, which is only a few footsteps away from here. It is more than 100 years old. It is no more. It has gone to see its maker. It is an expired lizard. It is a late lizard. However, its great-great-great-grandchildren are roaming across Western Australian desert. And look what a beauty it is. It has all these spikes on it, but it actually just eats ants, but it needs to defend itself against predators. I mean, most predators, they don't like to eat things with these spikes. But on the other hand, because of this, it also has difficulty getting water from a pond. But these spikes can help it to get humidity out of the air, and in this way get water. And also, when it stands in a muddy pond, water will go alongside its skin, alongside its integument, alongside the scales, from the feet, along the legs, all the way through its snout. So it's passive water transport. This is a process called capillary action, and we can use that as well.
Yes, and using these water techniques, we have designed amazing ways of collecting water that can be used within these hydrogen fuel cells. But we've also designed a water collection technique that has been sent up to the International Space Station.
Nature, the final frontier. The bone, the broccoli, the lung, the lizard, and so much more. Isn't it about time that we looked more closely at nature and tried to learn lessons from it to solve some of our engineering grand challenges and change the world? Thank you very much.
Broccoli, but there we go. So I would like to talk a little bit about the philosophy of engineering, but while that happens, you know, this is really quite grim, this. I don't know, you know, if you ever get to spend time in the back room of a museum where they keep all, like the basement of the Natural History Museum is one of the best places ever. Everything's in jars, and apparently Charles Darwin had really bad handwriting. But go on, take it away. Oh, and green gloves as well. Maybe you're doing a good advert for curators here. Yes, right. Now, I have a confession to make at this point in the evening, which is that I am not an engineer. But I am a part of the Department of Mechanical Engineering because it's a very broad church and because lots of things overlap. So I study the ocean and the planet, and what I would like to spend a bit of time talking to you about is some philosophy behind engineering. And we heard about many types of engineering. Perhaps something you were not expecting to hear about this evening is sewage engineering. So welcome to the poo talk. It's a very serious topic. Now, have we got any slides yet? No. Yes? Yes, hooray. So this is, I love this view of London, actually. So what you're looking at is a sort of top view of London with the city peeled back, and you can just see the topography. And when you look at London like this, you can recognize the shape of the river. But what you can really see is that the Thames is actually an estuary. It's a floodplain. This river has sort of made this wide, flat plain for itself on its way out to the sea. So this is how the Thames started out. It's just the drainage for 10% of the area of England. But then a city came along. This was our gateway to the ocean. And the problem with the brilliant thing about rivers is that they can carry things, people and, you know, all kinds of things, and they can also carry waste. So this is what Londoners did, right? As the city grew and the number of people grew and there were abattoirs and factories and all kinds of industry on the banks of the Thames, and if they had anything they didn't want, chuck it in the river. It's fine. It will get taken off down the river. Forget about the bit where the tide will bring it back 6 hours later. So over the centuries, the Thames just became London's sewer. And in the early 1800s, this problem got worse and worse and worse because people were chucking everything in there. The city was growing. And this is a picture from from a magazine of the day showing death, you know, rowing across the Thames, and there's all these sort of horrible dead things at the bottom. And Michael Faraday, he of the Royal Institution who invented the electric motor, being a very diligent scientist, went along to see how bad it was. And his experiment was that he tore up white bits of paper and he dropped them in the river. And he wanted to see how far down into the water they fell before he couldn't see them anymore. And he discovered they couldn't fall anywhere at all. And this is what he wrote. And it's a wonderful thing. He said, near the bridges, the feculence rolled up in clouds so dense that they were visible at the surface. The whole river was a real sewer. So basically, as the 19th century wore on, the Thames was just becoming stinkier and stinkier, and people were throwing more and more stuff in it. And this system that had just taken everything away somewhere over there stopped working. And it all came to a head in 1858, because there was a really hot, dry summer, and in July and August, the water in the Thames dried up till it was almost only a trickle, and all the filth and the feculence filled up this space, and it stank. It stank so badly that the members of the Houses of Parliament couldn't work. These, you know, lords and ladies, certainly no ladies, lords couldn't be doing with all this stink, and they put, special curtains. They tried to keep the stink out. But what the stink was telling them was that it was time to fix the problem. And it took the great stink for them to cough up the money to do it. So a grand scheme was cooked up, and this guy, Joseph Bazalgette, was basically the engineer who saved the day. And he oversaw, as the head of the Metropolitan Board of Works, he oversaw this enormous system of sewers. So he built, you've got the numbers here, 1,100 miles of drains underneath London streets, and they fed into 82 miles of brick-lined sewers. And the sewers took everything, instead of all the sewage going, into the river, it went into the sewers, and then it got carried downstream, and we'll get to where it went in a minute. But actually, the embankments are built on this today. So when you take on the district line through the Victoria Embankment, this is the tube line, that's the sewer. So those embankments were built to contain Bazalgette's great sewage system. So this was the great engineering revolution, right? There's a map here. The dark lines here show the different sewers. So this is all of London. And what the sewers were doing, they were getting bigger and bigger and bigger as you go this way. And up here, great big sewage outlets. This was where the sewage was pumped out into the Thames. So, and then the tide was just supposed to take it away. But actually, there was this was the biggest engineering project of its day. It was a huge endeavor. It took 20 years to get all this to work. And most of it couldn't be seen, but there were two places where it could be seen. It all flowed downhill under gravity, getting deeper and deeper. But then they needed to pump it back up to the level of the river in order to take it out to sea. And those two engine houses, one on either side of the river, where the pumping was done, are the only places where this enormous engineering project was visible. So they were really proud of them. And this is the Crossness engines. You can still go there today. I highly recommend it, especially if you've got any geeky engineer family coming to visit you. It's a great day out. Go and see the sewage engines. And it was known as the Cathedral on the Marsh because they were so proud of this whole system, but the only bit you could see was this bit. So they poured all their love and attention into it. And not only, so it's been restored, you can see this, it's painted red and green and gold, but what you can't see here is the detail, so that it's all decorated by cast iron figs. And they told me when I was there a couple of weeks ago that they've identified that the leaves on the sort of cast iron decoration are a plant which is good if you're constipated, shall we say. So they decorated it appropriately for the sewage works. Anyway, so the point is that this great engineering scheme was seen as the saviour of London because what had been happening was that the poor quality of the water and the high amount of sewage had been spreading cholera and typhus. Disease had been rampant through the city as well as the great stink. And Bazalgette's system took that all away. People stopped getting cholera, and so there's no doubt that this system saved tens of thousands of lives, if not more. There was a problem, and the problem is that Bazalgette's system never solved the problem. All it did was move it to some other place called away, which in this case was downstream out the other end of the Thames. But this was an example of kind of one-way thinking, like we make stuff over here, we're going to take it over there, it's just going to go that way, and then it just goes to away. And we never have to think about it ever again. But even at the time, there was a different way of thinking. There was actually, although Bazalgette built the sewers, there was a 20-year argument leading up to the choice of his system for the sewers. And the person on the other side of the argument was this guy, Sir Edwin Chadwick, and he has a connection to UCL because he wrote about the poor laws. He came to the attention of Jeremy Bentham, who was the philosopher and one of the co-founders of University College London, and whose slightly mummified remains are still in a box somewhere around the campus. He's moved a bit recently. I think he's in the student centre now. But he was making a philosophical point. It was all in the name of ideas. Anyway, so Edwin Chadwick came to his attention because he was writing about the poor law. Jeremy Bentham was into utilitarianism. How do we help people? How do we benefit the population? And Edwin Chadwick came along, took up Jeremy Bentham's ideas, and actually the Chadwick building here, the civil engineering building now at UCL, is still called the Chadwick building, and it's named after him. So what did he he thought Bazalgette got it wrong. He thought this system shouldn't ever have been built. And what he thought was that the system should have been different. Yes, there should be sewers, but what they should do is collect the sewage, store it for a while, and then move it back out onto the fields to fertilize the fields for the food that was going to come back and feed Londoners. He saw a circular system. And the 20-year argument was about whether the engineering was this sort of one way, we've solved the problem over here, therefore we're fine, or we've got a circular system which combines the whole thing. Now, Chadwick lost the argument, and Bazalgette's solution is baked into the infrastructure of London. We have a one-way sewage system. Now, it actually did cause problems. There's a whole other story about they had to start treating it because it did come back. But the point here is that, this is Edwin Chadwick's report that he wrote about, because he was concerned with the conditions for the poor. So here was a fundamental difference between these two people. Chadwick wasn't an engineer, but what he did do was he thought about systems. He thought about the whole system, whereas Bazalgette wanted a local solution for a local problem. And that is what traditional engineering has been. Where's our local solution? We're going to chop everything down, we're going to optimize it, we're going to constrain it, and we're going to solve this bit. But we now know that engineering has moved on. That partly because of the problems with our planet, plenty of other things, we need a much broader sense of engineering. You can see here today, all these people doing all these different things. They're not just thinking about a local solution for a local problem. They're thinking much more broadly. And so even though, this historical argument has been written about in terms of the difference. Is an engineer to solve the problem right here and not worry about the rest? Or is the job of an engineer to see how their solution fits into and improves the whole system? And so even though it was Bazalgette that built the sewers, I think Chadwick saw what engineering would become. Thank you.
Vehicles have long been envisaged as part of our daily life in future, predicted in various forms and iterations over decades. These vehicles that require minimal or no human interventions have captured our imaginations and featured predominantly in our dreams of futuristic cities. Here we are, in 21st century, in the year 2024, and we are still waiting. Where are they? Despite all of those predictions and advancements, fully automated vehicles are not yet part of our common reality. And some of you may wonder if they will ever arrive. I believe so. I believe that they will arrive. But this journey towards achieving this huge vision is with a lot of challenges. It has a lot of various and open challenges that engineers and researchers are working on to overcome. One of these challenges that we are addressing is understanding the cooperation between the automated vehicle and a human. This is a very critical and a key challenge to ensure a safe and seamless transition, especially when it comes to transition of fully automation to manual driving modes, when we have the introduction and definitions of various levels of autonomy. To tackle this challenge, we are making use of advanced sensors, such as EEG sensor, which allows you to monitor human brain. This data, as you can see in this video, allows us to have insights into humans' attentiveness, humans' responsiveness, and a state of awareness. We analyze these data sets, and with those, we are able to identify humans' attentiveness and the time that the driver is attentive and capable of taking back control from the vehicle in a safe and timely manner when it is required.
From these types of brain signals, we can go even further and convert brain activity into device commands, opening up possibility for human-robot interaction. This groundbreaking technology is known as brain-computer interface. With brain-computer interface, we can enable the direct communication between the brain and the external device, allowing for control of computers, prosthetics, and other assistive technologies fully through thought. This innovation not only enhanced the potential of automatic vehicles, but also revolutionized the way we interact with technology in our daily lives.
If we want to deploy automated vehicles, autonomous systems, robots into our society, we need bidirectional cooperation and communication. So Hubin and Bunny have talked about the human side of the interaction. In my lab, we're looking into going beyond what is available in today's vehicles and the feedback that is available, for example, audio feedback and visual feedback, and we make use of the sense of touch, which is called haptic feedback. So we have developed a haptic driving seat, which has soft robotic, pneumatically actuated robotic structures embedded all over. It's like a massage. And this seat can inform the drivers of non-urgent takeover requests so that they are safe and timely.
So you might think from listening to all this that we already have self-driving cars on our roads. But in fact, we don't, despite what some companies are trying to get you to believe. In fact, full-scale autonomy is probably quite a long way off still. Because first, we need to understand how humans, how users of self-driving vehicles are going to interact with the technology. So Seventh Sense Research, in collaboration with UCL and Loughborough University, are undertaking a pioneering new research program for the Department for Transport. In the first couple of stages of autonomy, you will be able to sit behind the wheel of your car and do other kinds of tasks. But you have to be ready to take back control if the car asks. We need to understand what types of tasks are safe for you to do that you'd still be able to take back control in a sort of timely fashion. Or if there are some tasks that are so immersive that it will be impossible for you to get back into the room, so to speak, in order to actually safely take control. You might be playing a game on your mobile phone and you've just got to that next level. Or maybe you're watching a movie and it's got to a really good bit. It doesn't look very safe. Human factors are the key part of the automated puzzle because we can program a system to be predictable, but we aren't. Our findings are contributing towards the development of the Automated Vehicles Act 2024, which will regulate and deploy self-driving cars onto our road. And we want self-driving cars. We want to realize the benefits, such as fewer accidents or more mobility solutions for elderly populations. Scientific research with the general population help us to understand how to regulate and deploy self-driving vehicles. Using rigorous data to inform policy decisions is exactly the kind of research that we're all involved in. And it's going to be putting safety at the top of the agenda before self-driving cars roll out onto our roads.
Sometimes it's an amazing place to be. You're getting the hang of that, right? Sometimes our colleagues ask us just to kind of help them with experiments. So it's nothing to do with us. They just want a person to do this thing, escape from a maze or eat some strange food that looks odd. listen to music and put headphones on for half a day. And we in general kind of put up with that and help her out as best we can. But sometimes, sometimes they do it to us and it really isn't. It feels like, they're actually not telling us something about this technology. They're not really telling me the truth about the kind of experiments they're doing. And these are the kind of things where,
You know what? You sound a bit traumatized.
I am a little bit traumatized by some of those things.
Do we need to take a moment, Mark? Where we're just going to it's okay.
Breathe.
Engineers do things to you sometimes. Sometimes it doesn't work out.
I know. I accept that at some level, but this is the whole ethics of engineering, isn't it? Like, there are things where we have to push the boundaries so the next generation can benefit. And
someone has to experiment.
Someone
has to be the guinea pig.
Yeah.
Yeah, we've both been the guinea pig, haven't we? I have a memory of standing on this stage, actually, with some large antenna on my head, with some neuroscientist behind me, and everyone was laughing, and I had no idea why. But it happens to you. But there is a thing about engineering which is genuinely about the spirit of experimentation and the spirit of failure. We all make that face, don't we? Sometimes you learn more by failing, but it never sounds quite as good. And we don't talk about failure very often as engineers, and yet we can learn so much from failures.
And failing is one of those things where I, obviously have done that a lot in my life, and it's quite hard to explain to our students that, join in with us, fail a lot, fail, and then you can put up with it.
Mark?
But sometimes it's just unacceptable, isn't
Mark?
it? Yeah.
What were you... You know that experimentation...
Yeah, that's what I'm talking about.
I think you need a nice cup of tea.
Yeah.
Come on, nice cup of tea. There's a nice place, there's a nice sofa you can sit down on, just over there.
What we have just seen on the screen is this baby monitor monitoring a baby and all the traffic that these devices is sending across the internet in just 20 seconds. This baby monitor in 20 seconds connected to 6 different destinations. The video for the baby monitor went to Google, Amazon, some other platform that is studying using AI you're sleeping, some other platform that is studying your action, and finally the baby monitor platform. All these destinations contacted, except one, are non-essential for the device to work. In fact, if we block all the 5 destinations that you see on top of this figure, we are still able to stream the video from this device. And this is not happening only with baby monitor, but actually any object nowadays can be connected to the internet. From smart speakers to doorbell, even your fridge can be connected to the internet. And we call this Internet of Things devices. And they are great. They make our life easier. But why they are so cheap? And what is the real value they give back to us? This is where my research journey started. I wanted to know what we are invisible trading in exchange to these devices. Because these devices have sensors on them. They may listen to you, doorbells may watch you, television may not know what you are watching. All of them send our data across the internet, sometimes unencrypted, leaving us vulnerable. But there is a lack of understanding of what information is sent and to who, and there is a lack of understanding of regional differences in regulations. For this reason, at UCL, we built one of the most advanced Internet of Things testbeds in the world, together with the one in Northeastern University in Boston. When we talk about privacy and security for Internet of Things, we need to think about 3 things. What if we are exchanging our privacy for minor gimmicks? What is sent from the smart home? Which information is exposed and to who? And what might this mean for the future. As an example, we can see that the majority of the data produced and sent over the internet from these devices in UK are not going to UK or Europe. They are going to different countries, third-party jurisdiction, where privacy regulation, like US or China, where privacy regulations is not the same as the one we have here in Europe. Why is this a problem? When all these devices and the manufacturer, the big tech, know so many things about you, it's easy for them to build a unique profile of the user. They cross-check this traffic from many devices that they have, and they may create a unique profile for you, influencing your choices from shopping to traveling, or which university you want to use. We will have a massive influence. Think about this Cambridge Analytica scandal, for example. And also your phone, your voice from the smart speaker. With your voice, it's easy to know your stress level, your gender, your age. The device that we know nowadays, like Alexa, they won't be there tomorrow. We will have machines that are much more advanced. So what will happen when these devices will become like a sort of like cognitive prosthetics, knowing everything about you and predicting what you would like before you know it? Your data today can influence the choices of your grandchildren tomorrow. Now that I really make you depressed, I want to say that there is a more bright future in my vision, where the control will be back to the user. We will have certification for these devices. At UCL, we are working on this. We are working on software that run on the home router and allow you to know where your data is going and to who, and what are the destinations that are non-essential for the device to work, and block them. We will have privacy and security labels for these devices, QR codes that will allow the user, before buying the devices, which are the security and privacy practices for them. I know that this will happen in the near future, but not so near, because some regulations like privacy and security certification will come in place in 2026. So until then, there are some small practices that you can have for like more privacy and security in your home. That is not like just throw away all your IoT devices at the moment. I'm sure that most of you will do it when you go back home. But for example, go to the privacy settings, read the privacy conditions, and opting out all the tracking and advertisement services that you have. Go to your smart televisions and opt out the automated content recognition practice. That is the one that allows the television to take screenshots of what you're watching and send to their service. Try to unmute the smart speakers when you're not using them, and try basically to unplug the television from the internet, for example, if you're just streaming on the air. I think that our future needs to be smart. Our future is already smart, but we need this smart future to be more private and secure for everyone. Thank you very much.
Mark's had his cup of tea, is feeling much better. Now, this event tonight is only one part of a whole week, a whole festival of engineering. And although we couldn't show you everything on stage, we just wanted to spend a moment to look back, to look at some of the other things that have been happening this week in UCL's Festival of Engineering.
And it's not quite the end. You may have been wondering what all this equipment is. Well, you're about to find out. Please welcome Fox
Dog Studios. We have learned many things this evening, and one of them is don't get hit on the head by a zero. We can all take that home with us. Yes. But what have been your highlights, Mark, from this evening?
Just don't let people, make you into a baby.
They're following us, apparently. Go on.
I think within reason, let people experiment on you, but in general, hold back from that. That's what I've learned.
I loved the astronaut and also seeing inside people's organs. That combination, they're all amazing. But that sort of perspective shift, I love that.
But that also just how much you haven't seen today. There is so much more going on in the faculty, and we want you to come and visit us again and see more next time.
But we are at the end of this show now, so, while you're winding down a bit, we do have some thank yous, because things like this don't happen without a lot of work from a lot of people, and we would like to credit some of those. So there were two organising geniuses behind this, Michael Riley from the Department of Mechanical Engineering, and Trent Burton from Cosmic Shambles, who we do a lot of work with sitting back there. Big round of applause for Trent. And if you are into this weird mixture, Mark and I do quite a bit of this, mixture of science and comedy and music, do check out Cosmic Shambles. We also need to give a huge thank you to the staff of the Bloomsbury Theatre here, because they've been really helpful today in setting up. Big round of applause for the staff at the Bloomsbury. And from we had a bit of applause for the lasers at the start, but I'd like to mention again Seb Lee Dalal, who gave that clip from his laser show Polaris. So he's still in the building. Big round of applause for Seb and the lasers. And then the next thank you goes. So all of these things take sort of big thinking from the top, and a lot of the credit for making the Festival of Engineering possible, as well as driving it forward, goes to the Dean of UCL Engineering, and that is Nigel Chichner-Hooker, who is in the audience. Please give him a big round of applause.
And of course, there is the festival team who really made it work, and that's Claire Elwell and Chris Neal, and my goodness, you've done a brilliant job. Yes, Claire! And Neil. And behind all them is an incredible range of professional services staff. I mean, we're all a team here at Engineering, and they really deserve a huge amount of credit. So let's hear it for the professional services, technicians. All the performers today, I'm sure you agree, they were absolutely brilliant. And let's hear it for everyone who performed on stage today.
One more applause for everyone who's been on stage.
And finally...
the festival is not over yet. Tomorrow is Saturday, and the exhibition over at 20 Bedford Way is in full flow tomorrow from 10 a.m. till 3 p.m. So if you've got, having been inspired by all of this, if you've got room for a bit more engineering, there are lots of hands-on things, lots of interesting things going on at the exhibition. So if you turn up there tomorrow between 10 a.m. and 3 p.m., you get hands-on engineering yourselves. But other than that,
thank you.
I think we are finished for this evening. So, most of all, what these events need is a really enthusiastic audience. So please give yourselves a massive round of applause and thank you from the Wonders and the Showcase. Thank you very much. Good night.